Hey everyone. I'm going to try this. Never done it before. So, what I'm going to do is, if you were gone last week, we went through Bernoulli's principle. I have an in class sheet. I can share that out with you guys if you were gone. I'll kind of run through a few of them. I don't know if I'll get to all of them just because it's a lot and you guys won't want to watch this. So, I'll try to get a few. Like I said, I've never done a screencast like this, and I'm going to try to be writing on it. And I'm using a stylus that's not going to be great. Hopefully, this will improve as we go on. But it's going to be me switching through stuff, and I'll do my best. So, all right. So, in like basically speaking, when we talk about Bernoulli's principle says that the faster a fluid moves, the faster the faster a fluid moves, the lower that pressure is going to be. Okay, so they're inversely proportional. So we this right here is flow rate. So if we have fluids flowing through a pipe, the amount of fluid flowing through that pipe is going to be constant no matter what we change the size to. So this is so if the area changes, then the velocity is going to change too. So when we talk about area, what we're really referring to is the radius changing, because if the radius changes, your area changes, and if your area changes, your velocity changes. Now, if your area doesn't change, then you don't have to do a flow rate problem because your velocity is not going to change. And that's what we're saying right here is if a variable is the same in both locations, you can cancel out the chunks that have that term in it. So when we talk about Bernoulli's, it's this really long equation that looks complicated, but it's really not that bad. Rho G H1 is equal to, and I'm going to run out of space here, so I'm just going to continue this down here. 2 squared plus G H2, and that should be a G2. Okay, so the idea is if your, for example, if your pressure is the same at location 1 and at location 2, then what we could do is we could cross off the chunks that had pressure in it. If we were to say, if I were to say that because my area didn't change, my velocity didn't change, then we could cross off the chunks that have my V's in it. Because my V1 and my V2 are going to be the same at both locations, we can cross off those chunks. Or we could go through and say if my height of my pipe doesn't change as a horizontal pipe, then we can cross off these chunks that have the heights in it. So that's Bernoulli's. Just to kind of really quickly talk about what these mean is when we talk about P1 and P2, I should have done this a little earlier in this video. That's talking about pressure. So pressure at location 1 versus pressure at location 2. This is our Greek letter for density, rho. So it's the density of the fluid. And when we're talking about the density of fluid, what we're really talking about is we're talking about water at 1,000 kilograms per cubic meter. Okay, so this is going to be the density of water. This is the density of water. This is the density of water, and this is the density of water. We don't ever use any other thing besides water when we are going through these. This is the velocity of the water at location 1, and then this would be the velocity at location 2. Don't forget that it's velocity squared. And then finally, the height at location 1 versus the height at location 2. Now, if it's a horizontal pipe, define your lowest point to have a height of 0. Okay. If we take a look at this is problem number 2 in the in-class problem. What we really said is we have this really big tank that has a little tiny hole on the bottom. And when we went through and we calculated this one, we have water flowing out. So we have a V2, and up here we can say, well, what's my V1? And we have an R1 and we have an R2 at these different things. this is really is a flow rate problem. And when we go through and we set this one up, we solve for my velocity at location 1. And what we find is our V1 is essentially, it's not actually, but it's essentially 0. It's some really small decimal. So what we kind of came up with, that is, if my R1 is much, much, much greater than R2, then we can say my velocity at location 1 is essentially 0. Now, it's not truly 0, it's just basically 0. Okay, so this is just a flow rate problem. This is not Bernoulli's yet. We were kind of using that as a lead into our last problem. So I'm not going to work through it, but the way we would do this one is this, because A1 V1 is equal to A2 V2, because it's a flow rate and a flow rate problem only. Okay, it's not Bernoulli's yet. So when we go through, this is number 3 on the in-class worksheet, a horizontal pipe. I would strongly encourage that as you're doing these, that we go through and we draw pictures. So we have a pipe that gets smaller, and we have location 1, and we have location 2. Now we have a radius at location 1, we have a radius at location 2. Things you're going to want on your picture is you're going to want P1s, you're going to want R1s, you're going to want V1s, and you're going to want H1s. You're going to want R2s, P2s, V2s, and H2s. Now, the reason why we want R1 and R2s is because that's how we're going to determine our area. So we have a pipe with a radius at location 1 is 0.08, and it is reduced to 0.044 meters. So it has water flowing through it at location 1 of 4 meters per second. And it has a pressure of 3 times 10 to the 5th pascals, which is 300,000 if you hate scientific notation, like I know some of you do. And ultimately what we're trying to do is we're trying to solve for what's pressure at location 2. Now, because this is a horizontal pipe, we can say that my height is constant. So we can define location 1 to have a height of 0. And if it's a horizontal pipe, we can also then state that my height at location 2 is going to be 0. And the really nice thing about that is then we can go through and we can cross off the chunks with the H's on it. So in order to do this first, though, we have to figure out what this velocity at location 2 is. If your area changes, then what has to happen is your velocity is going to change as well. If your area changes, your velocity changes. So we have to do an A1 V1 is equal to A2 V2 problem first. So because this is a circle, we got to go A1 V, we have to go pi R1 squared, because that's my A1, times my V1 of 4, and that's going to equal pi times R2 squared, because that's how we find our area at location 2, times my V2. Now, when you go through and you have 0.08 as your first radius, and then you have your second radius is 0.04, what happens is your radius got cut in half. Because it's a radius squared, it's really a factor of 4. And unfortunately, poor planning on my part, I don't have a calculator in front of me at this very second, but I'm almost certain, and I will verify this, but because my radius is cut in half, my area decreases by a factor of 4, which means my velocity is going to increase by a factor of 4. So we're going to get a velocity of 16 meters per second. Okay, so because of that, we can say my velocity at location 2 is equal to 16. Then we can go through and we can plug this into Bernoulli's. So Bernoulli's is that really long one, a P1 plus 1/2 the density times the velocity at location 1 squared, plus the density times our gravitational acceleration on Earth times our height at location 1, which is equal to pressure at location 2, that's what we're solving for, plus 1/2 rho, the density of water, times the velocity of the water at location 2 squared, plus the density of water times the gravitational acceleration on Earth times my height at location 2. Now, because this is horizontal pipe, and because we said my h's are 0 and 0, we can cross off my h's. Now, you could have said, hey, the height at location 1 is 10, the height at location 2 is 10. That's fine, but they're constant, so therefore we can cross off those chunks of stuff. That's the idea. We can cross off chunks. And then what we can do is we just really now, because I made this list of my variables here, and I made this list of my variables here, it's really now just a matter of like plugging stuff into our formulas as we go. So my pressure at location 1 is 3 times 10 to the 5th plus 1/2 times the density of water times my velocity squared at location 1, so that's 4 squared, which is equal to P2 plus 1/2 the density of water times my velocity squared. Okay, and then we go through and we solve this. And again, poor planning on my part, I don't have my calculator sitting next to me, so I'm going to do the best off screen on my phone. But what we'll go through, and so my pipe got smaller, right? My pipe got smaller here, so therefore my velocity increased. Now, Bernoulli says the faster a fluid moves, the lower the pressure. We aren't changing anything except for the height of, we aren't changing anything except for the radius of the pipe because my height is constant. So the faster a fluid moves, the lower my pressure. So my P2 should be smaller than 300,000, the 3 times 10 to the 5th. So if we take 3 times 10 to the 5th and we add it to 1/2 times 1,000, and we go through and we say, well, we take 300,000 plus 1/2 times 1,000 times 4 squared. When you go through and we add these numbers together, this left-hand side is going to be 308,000, which is equal to P2 plus, let me clear that, 0.5 times 1,000 times 16 squared is going to be 128,000. Okay, so now if we go 308,000 minus 128,000, we get a total, my P2, and I'm running out of space, so we're going to write it right here. P2 is equal to 180,000 pascals. That's my final answer. Okay, now this video is getting longer than I wanted, so I'll just try to set this one up, and that's about really all I'll do. I'll kind of leave it to you, and I can email the final answer on it, or maybe I might be able to. Again, I've never actually done this before. I might be able to hit pause and then like write the answer down. I'll figure this out as we kind of go. But again, we have a pipe with a radius of, so because we have a radius, that's going to give me, we can determine area based upon that. It has water that's flowing through it at 0.2 meters per second. The pipe goes up 0.8 meters, so we're getting a change in height, and the radius decreases, so it's going to get smaller. So in terms of a picture, I often will draw something kind of like that. Okay, so we have location 1, we have location number 2. Okay, we have location 2 right there. And again, things that we're going to want, we want to include things like P1, V1, H1, because we have an R1. So here we're going to want an R2, that's supposed to be the letter R, R2, P2, V2, H2. Now, if we say from here to here has a height of 0.8 meters, it would make a lot of sense if we define our lowest point to have a height of 0. So because that has a height of 0, we could say this has a height of 0.8 meters. Now, my velocity here is 0.2 2 meters per second. And then we could say, it says right here that the pressure at the second location, so this is 1.013 times 10 to the fifth. We're trying to determine what is the pressure at the first location. So my radius, last pieces that we have here are 0.11. This is 0.056. My radius changes. Because my radius changes, we have to do an A1 V1 is equal to A2 times V2 problem first. Pipe pi R1 squared, that's my area, times my V1 is equal to my pi R2 squared, 2 squared times V2. Again, I apologize. I'll get better at these hopefully as we go on and learn this process together. But when we go through, we can plug all this stuff in. And what's going to happen is that's going to give me a different velocity. Okay, so we're going to get some velocity right here at V2 that's going to be different than what we have over here at location 1. Okay, so when we go through and we set up Bernoulli's, now this would be a number. Again, I can do the calculation really quick. So if we take my radius, and I'm just going to do this again off screen, so 0.11 at location 1, my radius, times pi, I'm sorry, let me start over, pi times 0.11 squared times our velocity at location 1 is 0.2. And then what's going to happen is then I'll end up dividing by the area on this side. So it's pi times 0.056 squared. And then what we should get for what I'm getting for radius is not, velocity is not right. So let me try this again. Sorry. Pi times 0.11 times 0.2. Pi r squared times, yeah. So this I have on this side to be 0.0076. And then we have pi times 0.056 squared. So over here we get a value of 0.00985 times V2. So 0.076 divided by 0.00985, we get a V2 that when we don't round anything, I'm getting a value of 0.77, but without any rounding, we should be getting like 0.8. But that's what I got. Okay, so we'll just go with that. Then when we go through and we set up Bernoulli's is P1 plus 1/2 rho V1 squared plus rho GH1, which is equal to P2 plus 1/2 okay, so that's Bernoulli's. My pressure is what we're looking for, so my pressure is going to change. We're solving for, we're given P2, we're going to be solving for P1. That's what we're solving for. So the height at location 1 is 0, so we can cross off that chunk. My velocities change, my velocities change, so those stay, and I have a height at location 2. So P1 plus 1/2 times 1,000 times 0.2 squared plus 1,000 times 9.8. Oops, sorry. That's going to be 0 because that is 0 because this is 0. So I started filling it in, but my height is 0, so therefore that chunk is going to be 0. And that's equal to my pressure of 1.013 times 10 to the 5th. There is a decimal point right there. Plus 1/2 times 1,000 times 0.8. Oops, not 0.8. 0.77. Here, sorry, I shouldn't scribble. I have an undo button. 7 squared. So P1, that's my unknown, plus 1/2 times 1,000 times 0.2 squared, it's 20, is equal to, and again, 1.013 times 10 to the 5th is the same as 101,300. So 1/2 times 1,000 times 0.77 squared, and again, I shouldn't really be using that rounded value, but it's 296.45. I can't store my calculator or my phone calculator, so now when we go through, we're going to have to take this, we got to move it over to the other side. So we have 101,300 plus 296.45 minus 20. My P1 value is equal to 101,576.45. Oops. Shoot. You know what I forgot? I forgot that chunk. Okay, I forgot to add the height component. So this needs to be plus, I'm going to change colors because I forgot to do this. So this should be plus 1,000 times 9.8 times 0.8. Okay, so let me erase this piece right here. Okay, so this part right here, I forgot to do. So 1,000 times 9.8 times 0.8. This piece right here, is 7,840, which then gets added to this whole piece right here. Sorry about that. So we're going to subtract that 20 to the other side. So we're going to take 101,300 minus this 20. So then we're going to add that to the 296.45. And then we're also going to add 7840. And then our final answer, I apologize for that mistake, is 109,416.5 pascals. Now this is getting even longer than I expected, so my apologies on this. I said that at the beginning of the last one. When we do this problem, I'm not going to do this problem for you. The idea of this one is very similar to the in-class or the worksheet on the back side of your homework. The last two problems on the back side. This is going back to number 1, where R1 is much, much greater than R2. So we can say V2 is essentially going to be 0. I'm sorry, V1, the velocity at the top of my tank, is going to be essentially 0. So when you go through that, that's one key thing. The other thing to keep in mind is in the reading of this, a large tank develops a small hole. If both holes are open to the atmosphere, and what we're saying there is our P1 is equal to our P2. So in Bernoulli's, where we have that really long P1 plus blah, blah, blah equals P2 plus blah, 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 P1 and P2 are the same. So because those are the same, we can cancel those pressures out. Because our velocity on the top is 0. Now, what that really means is because the thing is so big, if you were to stare at the side of the tank, you would see it essentially not dropping at all. It wouldn't be moving. So that's why we use that assumption. Would it empty? Absolutely. Given enough time, this really big tank would run out of water, and we'd be done. So that's what this is saying. The velocity is essentially 0, is at the top. And you go through, you set this one up, and that's how you do it. So that's my first attempt of doing an explanation on this. It wasn't great. I know. I apologize. I'll learn. I'll get better. These aren't going to be perfect, just like I'm not perfect in class. I am working on getting Apple Pencil, so my stylus should be more reactive, and I should be able to do this a little better too. So we're in this together. If you need to contact me, please do. And I'll be posting some daily stuff here coming up too. So thanks for watching.